Hi guys, today we're going to go over section 16.4. We covered the properties of acids and bases yesterday. Today we're going to talk about acid strength and the ionization constant, Ka, for acids. So first of all, a strong acid, the definition of a strong acid is that it ionizes completely, which remember that we have let's do just a generic acid. So HA, the A can be any negative ion. For example, it could be Cl minus, which is chloride. So you'd have hydrochloric acid. A could be acetate, CH3COO minus. With the hydrogen, it would be acetic acid. So A is just any negative ion that you put hydrogen with, and it becomes an acid. When you mix that with water, H2O, you are going to get that hydrogen separating from the ion. So you would have A minus. So that negative is going to be produced as the H and the A come apart. The H plus will always stick to a water, okay, because these acid reactions are happening in water. If you don't have water, then they will not ionize. They will not be able to separate. So it's always happening in water, and anytime you have H plus floating around, it's going to stick to a water. And we kind of skipped over this yesterday, so I can come back up here really quickly. Hydronium is the product that forms. So this was part of yesterday's section. I've added this, so it wasn't here. We have to know what hydronium is, and you should kind of be familiar with it. H3O plus is hydronium. And all that is you have H2O. So let's say, here's our Lewis structure for H2O. And you have an H plus floating around. If you put these two together, 100% of the time, they're going to stick together, and what you get is H3O plus. Okay, so this guy right here, this is my hydronium ion. Okay, so down here, when the H separates from the acid, you have H plus floating around, you add it to the water, and you are forming H3O plus. Okay, the lazy version is saying acids give off H plus, that's our proton. Okay, what's actually happening is that H plus is produced, but then it's immediately turned into hydronium, H3O plus. Okay, so strong acids ionize completely. Weak acids only partially ionize. Partially ionize, meaning if you have, let's say, 100 of these, in a strong acid, 100 of each of these would be formed as they separate. If it's a weak acid, it's only partial, and it really depends on the acid, but for some of them, it's just like only 5% of the acid, the HA, will actually separate. Okay, so they partially ionize, and that is over here in your book. Definition of a strong acid is it completely ionizes, where a weak acid only partially ionizes. Okay, and here's that generic reaction where HA is my acid. When you add it to water, you get H3O plus. I should have put AQ for aqueous because it's dissolved in water, and A minus aqueous. Okay, for strong acids, you will have a single arrow, meaning the products are 100%, so there's no reactant left. So if we tried to do an equilibrium with that, the reactant would be 0. That would be 0 on the denominator, and it doesn't exist. So that's why we use a single arrow. It's all product. That's the only thing that's made. If I have HCl, that's an example of a strong acid. Let's come back over here. If I have HCl, plus H2O liquid, that is going to form single-sided arrow H3O plus and Cl minus, and that's going to happen 100% of the time. It's technically not 100%, but it's close enough that we're going to call it 100%. So what that means is if you have a 1 molar HCl solution, then 1 mole per liter of H plus is going to come off of it. And that H plus is the same as 1 molar H3O plus. H plus is just kind of the lazy version of acids. Okay, so all of these are true. If you have 1 molar HCl, you have 1 molar H plus, you have 1 molar H3O plus. Okay, and that's because it ionizes completely. So every pair HCl is going to separate into its ions. Okay, we have 3 definitions that are pretty easy: monoprotic, diprotic, and triprotic. The protic part, the second part, just means proton. And remember, a proton is that hydrogen atom that's lost its outer electron. And so H plus is the atom without the electron around it. So it just is a proton that's left in the center. So we can say H plus, hydrogen ion, or we can say a proton. They mean the same thing. Mono, of course, means 1. So monoprotic means 1 hydrogen is detachable or removable. 1 hydrogen, let's call it ionizable. It's able to be ionized. Diprotic means 2 hydrogens. 2 hydrogens are ionizable. And an example of that would be carbonate, carbonic acid. Example, H2CO3. Carbonate is CO2 minus. With the hydrogens, it becomes carbonic acid. And both of those hydrogens are able to be ionized and form H plus floating around, which will then attach to water and make H3O plus. So 2, anytime you see these 2 hydrogens, it's going to be diprotic. Triprotic, 3 hydrogens are ionizable. There aren't very many triprotic acids. I'm getting ahead of myself. H3PO4, phosphate PO4 3 minus, will turn into H3PO4 as an acid, which is phosphoric acid. And those 3 hydrogens out in front are ionizable. So that is a triprotic acid. Okay, so the prefix tri tells you the 3. Product tells you it's hydrogen. Here is a little trick that I got from another AP Chem teacher. You have to memorize the 7 strong acids. Okay, 7. Oh, I'm lying. AP Chemistry changed it to only 6. So yes, we have 1 less to memorize. 6. One of them, this one right here, they've removed. So 6 strong acids. If you like little mnemonic devices, you can use this. If you just want to memorize them, that's fine too. They are HBr, HCl, HI, and then HNO3, which is nitric acid. So you have hydrobromic acid, hydrochloric acid, hydroiodic acid, nitric acid, HClO4, that's perchloric acid, and then H2SO4, that's sulfuric acid. So these are the 6 that you have to memorize. I thought this was kind of cool if you like them. If you remember the saying, "So I brought no clean clothes," you went to your friend's house and you brought no clean clothes. I don't know, however you want to remember it. The SO is for the sulfate. So see this SO. that's H2SO4. The I is for the iodide, HI. Brot, that's from the bromine, so hydrobromic. No, that's for the nitric acid, NO3. Cl, that's for the hydrochloric acid, HCl. And clothes, ClO, is for that ClO4. HClO4 is perchloric acid. So that might help you. So I brought no clean clothes. Those are the 6 strong acids that you have to have memorized for the AP test. Okay, you will definitely need that information. And if it's not one of those 6, the good thing is you can assume that it is a weak acid. If it's not one of the 6 strong acids, then it's automatically considered a weak acid. Okay, we will also need to know the strong bases, but we'll come back to that. Okay, a weak acid. Notice that this is a lot of the halogens. We have chlorine, bromine, and iodine. Fluorine is not on our list of strong acids. That's because it's so tiny. We have F. It has 9 protons and 9 electrons, so 9 positives and 9 negatives. Hydrogen is also tiny with its little 1 proton and 1 electron. Because fluorine has a pretty large positive charge and it's such a small atom, the coulombic force, okay, the size of the atom and the charge, is so great that hydrogen really likes to stick to it. So that hydrogen and the fluorine, they stay together. And that's why it's not a strong acid, because only some of the hydrogens will separate and a lot of them will actually stay together in water. So it's a weak acid because it doesn't ionize completely. And that's because it has a great coulombic attraction between the F and the H. They're really stuck together like a strong magnet with a strong magnet. Okay, so it's a weak acid. So if I mix that with H2O, I'm going to get an equilibrium. That's supposed to be an arrow pointing that way. So we have a double-sided arrow here going each direction. Some of the H's will come off, but very few. And when they do, they will stick to water. So we have H3O plus and we have F minus. And I'm making up numbers here. So let's say if you had 100 HF and you put them into water, maybe only 5 of them will ionize. And that means that you'll have 95 of those HFs still just floating around together as a compound, not separating. Okay, now, those are not real numbers because we never count 100 little compounds. We're going to have a certain concentration, a lot of them, like moles, right, which is 10 to the 23rd. We have trillions and trillions and trillions of these little HFs in there. So how do I know exactly how many will really ionize? It's not going to be 5. Okay, so these are made up numbers. The way that we know how many actually ionize is by the acid ionization constant, which we call Ka. And guess what? This is just an equilibrium constant. Okay, so we're going to write the equilibrium constant for these guys. And basically from here on out, we have a lot of equilibriums and a lot of ice charts. So if you forgot how to do those, go back and review your ice chart videos. Okay, going back to our generic equation. So HA, where A can be any negative that you put it with, and this can be a strong acid or a weak acid. When you mix this aqueous acid with H2O, which is a pure liquid, you can have an equilibrium. So this is not the strong acids. And you will form H3O plus as that hydrogen sticks to the water, and you will have A minus, and both of these are aqueous, and I should have put that AQ because it does in fact matter here. Okay, so this is just an equilibrium reaction. So it's been in solution for long enough that all of the H's that are going to come off have come off, everything has reacted, and the reverse reaction is also possible, where the H pluses will rejoin the A minus and it will reform HA. So this is a reversible reaction. It's going on at equal rates. We're at equilibrium. If I write the K, normally I would put a little C here for concentration. It would be my product. That's H3O plus and A minus over HA, And here's the trick. This is a pure liquid, so that's not part of my equilibrium expression. And because these are a special type of equilibrium where we have acids involved, we actually change the subscript from concentration to A for acid, but nothing else changes about it. This is just an equilibrium expression. Okay, there is a lazy version. Instead of putting H3O plus on top, sometimes you will see H plus, which is equal to H3O plus. They are one and the same concentration, so the number is the same regardless. Okay, this is the lazy way of writing it, so you will see that sometimes. Okay, so what does that mean? That means that I can judge how much product is going to be given off if I know the Ka values. For example, let's look in your book. Okay, down here, your book has a table listing the strong acids as well. If you want to use that to study them, you can. Okay, so, and then they have these little diagrams. Look at the strong acid. All of the HCl that they're adding here is going to separate into Cl minus and H3O plus, and they show you the little diagrams there. This is a weak acid where when you add HF, you have some HF left over at the end. So this is going to be an equilibrium here. Okay, for weak acids, you have that equilibrium arrow. There's our triprotic. Here's just some random examples of weak acids. You don't have to memorize that table. And here's what I was talking about. So see, they've written the equation both ways, H3O plus and H plus. It's the exact same equation, and you will get the exact same Ka value no matter which one you put in there. Here are some values. So chlorous acid, HClO2, has a Ka value of 1.1 times 10 to the negative second. I'm going to write that over here. Ka, let's see, if Ka equals 1.1 times 10 to the negative 2, no units on this guy, then what does that mean? That means that you have, it's approximately equal to 1 over 10 to the second, which is 100. So it's approximately equal to 1 over 100. That means that if you had 100 reactants, you'd get like one product. So it's about a 1% ionization. This is a very rough approximation. If I look at something else, let's go down here. Ooh, this is vinegar. Acetic acid, HC2H3, O2 right here, acetic acid. This is Chaku with the hydrogen attached to it. So this H at the end is the only one that comes off. The H is bonded to the carbon will not come off. So those are not part of the acid. And it's 1.8 times 10 to the negative fifth. 1.8 if Ka 1.8 times 10 to the negative fifth. If Ka is that value, that's about 1 over 10. 10 to the sixth is a million. So 10 to the fifth would be 100,000, I believe. Oh yeah, it's just however many zeros as the exponent. Now I'm awake. So that is, ooh, what percent ionization? A very, very, very small. Very, very few H plus ions are ionized or separated. So if you have a very small Ka, that means that you don't have a lot of H plus and A minus. If you have a bigger Ka, which this is not a huge number, but it's definitely bigger than this one. So a bigger Ka means you have more H plus. They're ionized more than they are staying together. Okay, so we can judge how strong an acid is by its Ka value. Way down here, phenol, for example, this is a benzene ring with an OH attached to it. So phenol, a phenyl group with an OH, an alcohol. has a Ka of 1.3 times 10 to the negative 10th power. That's less than a billionth of them separating. So this is a very, 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 very weak acid. And then as you go up, see the exponents of 10 get less negative. They get larger. So 10 to the negative 2. This is the strongest acid on this list. Chlorous acid is the strongest. And then they get weaker and weaker as you go down. Okay, so the Ka value, let me summarize that up here. Okay, the value of Ka tells us the relative strength of an acid. Okay, small Ka, like we had here, this is very small, equals very weak acid. A large Ka, relatively, so we're not talking about 10 to the positive 6th, but if we have something that's larger, call it a larger Ka, equals a stronger acid. Strong acids would have a Ka that when you have all product, so for a strong acid, let me use yellow, this would be like all of it, and this would be basically approaching 0 as you have none of them together. That means that this is approaching infinity. So they would be ridiculously large, like 10 to the 56th power. Okay, so Ka that they're undefined. They approach infinity. Okay, and those of you in calculus, that makes more sense to you, but just know you cannot divide by 0. You can't do that. So that's why you can't really have a Ka value for those strong acids, and that's why you won't see them on the chart over here. These are all weak acids. So you're just comparing different weak acids. So of the weak acids, chlorous acid is the strongest weak acid, and then phenol would be the weakest weak acid. All right, we will discuss this more tomorrow. Have a great day. I'm going to check that we're done. Oh, I wanted to look at these before we move on. Conceptual connection 16.2. Consider the 3 generic weak acids, HA, HB, and HC. They're made up. The images show the ionization of each at room temperature, which has the largest Ka value. Pause. Pick an answer. All right. So for A, I see 1 hydrogen ion. That's our product on top. B, I see 1, 2, 3, 4 hydrogen ions. That would be on top. And for C, I see 2 hydrogen ions. So the order is HB has the greatest Ka value because it has the most H+. And if I found them, if I hunted them down, it would have the most of these B-, B by themselves. And then HC is the second highest because it has 2 hydrogen ions. And HA is the weakest because only one of those hydrogen ions has separated. Conceptual connection 16.3, relative strength of weak acids. Consider these 2 acids and their Ka value. HF, Ka is 3.5 times 10 to the negative 4th. HClO, Ka is 2.9 times 10 to the negative 8th. Which acid is stronger? Pause. Pick your answer. Correct answer is HF is a stronger weak acid than HClO. Okay, because the 10 to the negative 4th makes this top number a larger value than the bottom one. All right, now I'll see you tomorrow. Bye-bye.